Welcome to our presentation on 3GPP Technical Report 22.865, focusing on the study of satellite access Phase 3 for 5G systems. Before we dive into the specifics, let's briefly discuss what Phase 3 specifications typically entail in the 3GPP ecosystem. Phase 3 specifications in general represent a mature stage in the development cycle of a technology within 3GPP. They usually incorporate advanced features and optimizations that build upon the foundations laid in earlier phases. In the context of 5G and satellite integration, Phase 3 is expected to address more complex scenarios and use cases that weren't fully explored in previous phases. These specifications often include integration with emerging technologies, pushing the boundaries of what's possible with the current system. For satellite access, this might involve advanced inter-satellite communication, enhanced mobility management across satellite and terrestrial networks, and more sophisticated resource allocation techniques. Performance enhancements are a key focus in Phase 3 specifications. This could involve improved efficiency in satellite terrestrial handovers, reduced latency in satellite communications, and better energy efficiency for satellite-connected devices. Lastly, Phase 3 typically address cross-functional system improvements, looking at how satellite integration affects various aspects of the 5G system as a whole, from core network operations to end-user experiences. This holistic approach ensures that satellite access becomes a seamless, integrated part of the 5G ecosystem. Today, we'll be exploring the integration of satellite technology into 5G networks and its implications for future mobile communications. We'll begin with an overview of satellite access in 5G, discussing its importance and the key areas of focus in this study. We'll then delve into various use cases that demonstrate the potential applications of this technology. Next, we'll examine specific technical aspects, including store and forward operations, UE to satellite to UE communication, and GNSS independent positioning. We'll also discuss other important considerations such as efficient communication paths, usage statistics, and security measures. We'll then look at the charging aspects of satellite integration, which present unique challenges in billing and resource management. Following that, we'll review the consolidated requirements derived from our analysis, which will serve as a foundation for future standardization efforts. Finally, we'll conclude with a summary of our key findings, their importance for future 5G development, and recommendations for next steps in the standardization process. Throughout this presentation, we'll be exploring how satellite integration can enhance the capabilities, reach, and resilience of 5G networks, opening up new possibilities for global connectivity. Let's begin. This slide serves as a comprehensive reference overview slide. I won't get into the details of this slide. Feel free to pause the video here if you like to examine the subtopics. This will provide you with a clearer roadmap of the content as you progress through this presentation. The scope of this study is comprehensive, addressing several crucial aspects of satellite integration in 5G systems. First, we'll explore store and forward satellite operation, a key feature for enabling communication in areas with intermittent satellite coverage. This is particularly important for IoT applications in remote locations. UE to satellite to UE communication is another focal point, investigating how devices can communicate directly through satellites without involving ground networks. This capability could revolutionize emergency communications and enable new applications in maritime and aviation sectors. This study also delves into GNSS independent operation. We'll take a closer look at what that is in specific when the slide comes up. Recognizing that not all devices may have access to traditional GPS or other global navigation systems. This is crucial for ensuring ubiquitous 5G coverage and services. Positioning enhancements for satellite access are explored, aiming to improve location accuracy and availability in challenging environments where terrestrial solutions may fall short. These focus areas address critical challenges in current 5G deployments. By enabling delay-tolerant services, we can support applications that don't require real-time communication but need reliable data transfer. Direct device communication via satellite opens up new possibilities for connectivity in areas beyond terrestrial network reach. The importance of satellite integration in 5G cannot be overstated. It promises to extend 5G coverage to previously unreachable areas, including remote terrestrial locations, maritime zones, and airspaces. This integration also provides a robust backup for terrestrial networks during natural disasters or other emergencies. Furthermore, satellite integration enables new IoT and M2M applications. M2M is machine-to-machine applications that require global coverage, such as asset tracking across oceans or environmental monitoring in remote areas. It also supports critical communications for industries like aviation, maritime transport, and emergency services, ensuring connectivity where it is most needed. As we progress through this presentation, we'll explore how these aspects come together to create a more robust, versatile, and globally accessible 5G ecosystem. Okay, on this slide, there are many use cases listed here. They are diverse and impactful. Feel free to freeze the video here to go through them if you'd like. I won't read through all of them one by one, but I'll point out a few. Store and forward operations enable communication in areas with intermittent coverage, crucial for IoT applications in remote locations. UE to satellite to UE communication revolutionizes emergency response and enables connectivity in areas beyond terrestrial network reach. Enhanced positioning services improve location accuracy in challenging environments, benefiting autonomous vehicles and search and rescue operations. LAN, local area network using satellite access, provides connectivity solutions for temporary or remote operations such as scientific expeditions or offshore platforms. Well, I might as well go through the rest of it. There are 4 more. The next one is information exchange between ships at sea enhances maritime safety and efficiency. UAVs, unmanned aerial vehicles using satellite access, can operate over vast distances, aiding in emergency response and remote area surveying. Service differentiation via satellite access ensures critical communications are prioritized, and diverse user needs are met. Finally, vehicle fleet management in remote areas like deserts benefits from continuous connectivity for tracking, maintenance, and route I'll say route from now on, optimization. These use cases, and I went through all of them. I thought I would just point out a few, but actually there aren't that many. So these use cases demonstrate how satellite integration expands 5G capabilities across various industries and scenarios. Store and forward satellite operation, SNF in short, is a fundamental feature for enhancing the reliability and reach of 5G systems through satellite integration. It allows the satellites to temporarily store data when a direct connection to the ground network is unavailable, forwarding it when a feeder link becomes available. We'll take a look at all these different links: feeder link, service link, inter-satellite links. We'll have pictures later on to illustrate all these concepts. This capability is crucial for communication in areas with intermittent satellite coverage and for delay-tolerant IoT applications. Key requirements include notifying UEs of SNF mode activation, configurable retention periods and storage quotas, QoS policies for stored data, and secure data handling. The system should also support prioritization of emergency data. Application scenarios are diverse, including remote environmental monitoring, maritime and aviation reporting, disaster area communication backup, and health monitoring in isolated communities. SNF satellite operation significantly expands the utility of 5G networks, making them truly global and resilient communication systems. So here are two diagrams on this slide. I put them together so that we can compare and contrast them. The top one depicts these are satellite operation modes. So there are two of them. One is the normal default mode, and the other is SNF mode, store and forward mode. So the top one depicts the normal mode, normal default satellite operation mode. The bottom one is the other one. So let's take a look at the top diagram first. And for all diagrams, I'd like to first take a look at the elements. What are the elements quickly on the picture so that we can immediately spot what we're looking at. So first of all, the elements. We see a satellite. We see a satellite represented by a stylized satellite icon at the top of the image. It acts as the intermediary for communication between ground-based elements. We have a service link, the connection between the satellite and the UE, and is represented by a dotted line, dotted line indicates wireless connection. We have a feeder link, the connection between the satellite and the ground network, and is also represented by a dotted line indicating wireless connection. We have UE. The UE is shown here as a Wi-Fi icon labeled as UE, for example, IoT device. That's a label. It represents the end user device. In this case, an IoT device, any IoT device can be the endpoint. The ground network is depicted as a satellite dish icon. It represents the terrestrial infrastructure that interfaces between the satellite network and external networks. The external network and IoT service endpoints are shown here as a cloud icon. So it's labeled as such. And it represents the broader network infrastructure and specific IoT services or applications that interact with the IoT devices. The signaling and data exchanges are represented by this big green arrow. On the second picture, there are two big green arrows. spanning from the UE to the external network. It indicates the flow of both signaling data, which is the control data, information, and data between the IoT device and the IoT service point. So control data and the payload of regular data. So the data path and the control path are both indicated by the green arrows. So what is this showing us? The diagram shows how an IoT device can communicate with its corresponding application server in the cloud, in the ground station, through a satellite network. The satellite acts as a relay point, bridging the communication between remote IoT devices and the ground network. So the two communication links, there's a two-stage link. The communication is divided into two main links, I should say. The service link, which is device to satellite, and the feeder link, satellite to ground network. The satellite appears to operate in a so-called quote-unquote bent pipe. That's a special acronym. It's like transparent mode, similar to transparent mode, which means simply relaying signals between the ground segments without onboard processing. It's not processing the data, it's just like a pipe. It's called bent pipe. The ground network interfaces between the satellite system and conventional terrestrial networks, allowing seamless integration of satellite-based IoT devices with existing infrastructure. This setup is specifically designed to support IoT use cases where devices in remote or widespread areas need to communicate with centralized application servers. The green arrow, again, I'm looking at the top diagram now. The green arrow suggests that communication can flow in both directions. So it's bidirectional communication, allowing for both data collection from data devices and command and control signals sent to the devices. Okay, what about the bottom diagram? The bottom diagram has all the same elements. I won't go through them, but we have two satellites. We have two satellites on top. They're labeled as step A and step B, and it indicates a two-step process in the communication here. So we have two green bent pipes instead of one. So with all the same elements, what is it doing here? It works as follows on the second diagram. Step A, the UE, the IoT device, sends data to the first satellite. The satellite stores this data on board. This is indicated by the upward green arrow from the UE to the first satellite. Step B, the satellite moves to a new position where it has visibility of the ground network now. So the satellite now sees the ground network. The stored data, the previously stored data, is then forwarded to the ground network because it can do so now. This is shown by the downward green arrow from the second satellite position to the ground network. The data is then passed on to the external network IoT service endpoints to be processed. So this is a store and forward scenario. The way the mode is that the satellite temporarily stores the data from the UE before forwarding to the ground network. The idea is very simple, right? You store it first because you can't send it to the ground network because the satellite doesn't see it. But once it sees the ground network, has the connection there, then it forward the data through. That's the idea, basically. Now, a few things I want to point out. This mode allows for communication even when the satellite doesn't have simultaneous visibility of both the UE and the ground station because it does delayed transmission. It has logic. The implementation is that it is clever enough or intelligent enough to store something first and just do communication with the IoT device, just like normal communication. And then once it has a connection to the ground network, then it forward the data there to be processed. It's very transparent. The band pipe is operating in a transparent mode because of this delayed transmission. Now, this approach is suitable for non-real-time applications much more than real-time applications, as you can imagine, because there are some delay in data delivery, and the non-real-time communication allows for delay. The delay in delivery is acceptable in non-real-time communication. That's why it's more suitable. This also enables communication with devices in very remote areas that may only have intermittent satellite coverage. We are really using the satellite efficiently this way as well, because data can be collected from multiple devices during one satellite pass overhead, and then delivered during another pass over a ground station. The pass here is satellite pass overhead, above where the satellite is moving along. So this mode can be energy efficient for IoT devices, as they only need to transmit when the satellite is overhead. So this is suitable for low power devices in specific. It also allows for a more flexible network design, especially in areas where challenging geography or limited ground infrastructure. So we're talking about a very flexible network topology. Okay, that's all for this picture. The next one also have two diagrams that I put together side by side so that we can look at them together. These two diagrams illustrate the concept of serving satellite change during feeder link disconnection. When we don't have a feeder link, what happens? So the diagrams here depict two scenarios, one where the IoT device is moving and the other one when the satellite is moving. So let's take a look at the elements quickly. We have the IoT device on each picture on the bottom there. They represent a delay-tolerant device, such as sensor or tracking device. We have satellites A and B. These are part of a low Earth orbit constellation. Low Earth orbit is LEO, so-called LEO, which is an acronym for Low Earth Orbit constellation. We have gateways. These are ground stations that connect the satellite network to the terrestrial network. We have service link connecting the IoT device and a satellite. We have feeder link connecting a satellite and a gateway. We talked about these links before. We have the third link, which is inter-satellite link here, which connects two satellites. So the left diagram, which is labeled IoT device moving, this scenario shows the IoT device moving from the coverage area of satellite A to satellite B. The feeder link between satellite A and the gateway is disconnected. You can see that it's indicated by a big red cross. That's disconnect. That's indicating the feeder link between satellite A and the gateway is severed or disconnected. As the IoT device moves, it transitions to being served by satellite B, which has an active feeder link to the gateway. Now let's take a look at the right diagram, which is labeled satellite moving. This scenario depicts a static IoT device, but the serving satellite changes due to the movement of the satellites in their orbit. Initially, satellite A serves the IoT device but has a disconnected feeder link, also indicated by this big red cross that you can see. As satellite A moves out of range, satellite B takes over, serving the IoT device, and has an active feeder link to the gateway. So in both cases, the inter-satellite link between satellites A and B is crucial. It allows for the forwarding of stored data from one satellite to another, ensuring continuity of service, and continuity of service is a requirement, and eventual delivery of the IoT device's data to the ground network. This setup demonstrates the store and forward capability in satellite networks. When a feeder link is unavailable, data from the IoT device can be stored on the satellite and then forwarded either when a feeder link becomes available or through inter-satellite links to a satellite with an active feeder link. Okay. We have several more diagrams coming up. These are use cases. They're very interesting use cases that demonstrates how this technology can be used. So this next one is an image illustrating the concept of animal tracking in the remote areas. What is depicting is a scenario where satellite communication is used to facilitate wildlife research and monitoring in very remote locations. So what are we looking at here? We have remote area number 1, represented by an image of a bird or some kind of flying creature. This likely symbolizes a wildlife habitat or study area. We have area number 2, which is depicted by an image of a penguin. That is a penguin, unmistakably so, a penguin. It represents another remote location, possibly in different ecosystem or geographical area, for example, in the North Pole or something. We have the scientific center shown here with an image of server racks or data centers. This represents the research facility where data is collected and analyzed. There are 3 satellite icons at the top of the image. These satellites form the communication link between the remote areas and the scientific center. The scenario here involves using satellite communication to collect data from IoT devices or sensors on the IoT devices installed on animals in remote areas where there is no terrestrial network coverage. So what is it doing? How does it work? Sensors are usually installed on animals to collect data about their movements, physiology, and surrounding environment. These sensors send status information to satellites when they pass overhead. The satellites store this information and forward it to the scientific center when they have an available feeder link to the ground network. This store and forward mechanism allows for data collection and transmission even when there is no continuous connection between the sensors and the ground station. The scientific center can then analyze this data for research purposes such as studying animal behavior, migration patterns, or environmental conditions. So this is an interesting use case that's being done a lot everywhere now already, of course. Okay, next picture. There we have several coming up. This one illustrates the concept of LAN, local area network using satellite access. So what is it saying here? So let's take a look at what are the elements on the picture. We have area, loc area. Loc area actually is short for local area. I don't know why it's shortened that way. It's a bit confusing. This represents the remote location where the scientific expedition is taking place. It contains a ship or a boat, because it's kind of small, a boat, likely representing the expedition vessel. We also have multiple mobile devices representing the explorer's equipment. A satellite dish for local communication with the satellites. The LOC data center, which is short for local data center, a green box. My picture has the color green, but I don't know, the slide does not show it very well. The LOC DC stands for local data center, which is a green box representing the local scientific research station's data center. On the other area, which is labeled area RAM area. RAM area is actually short for remote area. This represents the area where the main scientific data center is located. It contains a satellite dish for communication with the satellites. It also has a 5G core, representing the 5G core network infrastructure is also there. RAMDC, Remote Data Center, is the main scientific data center. So we have also multiple satellites are shown on the top here, forming a constellation. These satellites are connected by ISL. ISL is short for inter-satellite links, allowing them to communicate with each other. We have feeder links, we have server links, also in the picture, which we have talked about. Now the server links here are represented by the lightning bolt symbols. Lightning bolt. Those are service links, showing communication between the mobile devices and the satellites. The scenario here involves a scientific expedition team conducting research in a remote area where terrestrial network coverage is unavailable. The remote area here is the LOC area, LOC area. So what happens here is that the expedition team uses satellite access to establish a LAN, a local area network, in the remote location. The local scientific research station, LOCDC, supports data analytics and research in the remote area. The RAMDC, the Remote Scientific Data Center in RAM area, served as a terrestrial operator, supports further data analytics, and retrieves all data and research results from LOC data center at fixed times. Satellite access enables communication between the devices in LOC area and allows data exchange between LOC DC and RAM DC, the local DC and the remote DC. The system supports flexible network configuration, combining satellite and terrestrial elements to provide continuous connectivity. As the expedition moves or when terrestrial coverage becomes available, the system can dynamically switch between satellite and terrestrial access to maintain optimal connectivity. So this is the beauty about it, is that it can dynamically switch between satellite and terrestrial access. It's implemented that way, and it needs to be implemented that way. Because satellite service, after all, is still not inexpensive. Let's put it that way. Okay, so this is what it is. This showcases the potential for creating very flexible network. You may call this a hybrid network. Because we combine satellite and terrestrial elements to support scientific research and other activities, and you can switch between the two. So this could be described as a hybrid network. Okay, the next image illustrates the concept of communication via the same satellite without going through the ground network. This is a simple diagram. We are seeing two ships, ship number 1 and ship number 2. They're depicted on the high sea as if they're moving, representing vessels in open waters, far from land. We have a single satellite above the ships that is providing communication coverage for the area. We have the core network represented by a cloud icon labeled core network, and that is on land. So the communication links, we have solid lines, so the solid lines connecting the ships to the satellite representing direct communication links. A solid line also connects the satellite to the core network on land. What you're seeing here is describing ships communicating with each other at sea using satellite communication. The primary feature illustrated here is the ability for the two ships to communicate directly through the satellite without routing the traffic through the ground-based core network. This is really a very efficient way to communicate because it allows direct communication via the satellite. The system reduces latency and improves efficiency, especially important for time-sensitive information exchange between ships. And also, it is independent from terrestrial infrastructure. This setup enables communication in areas far from land, where traditional terrestrial networks are not available whatsoever. And of course, this is giving us a very flexible way to configure our network. The direct communication capability is particularly valuable for maritime safety, allowing ships to quickly exchange information about weather conditions, potential hazards, or emergency situations. So this is benefiting maritime applications enormously. Next, this is slightly different. We are seeing more or less the same elements, but the idea is very similar. We have 3 ships here depicted on actually 2 ships, with ship number 1 and ship number 2, but ship number 2 moves. So it's actually 2 ships, but ship number 2 moves from one location to the other and is being shown here as moving, indicated by the arrow. We have 2 satellites instead of 1 in the previous diagram. Now shown here, providing communication coverage for the area. We have the core network. On land, we have the ISL, inter-satellite link. What else do we have? Of course, the solid lines, the communication links connecting the ship to the satellites, also connect the satellites to the core network on land. So you can see all those connections by the arrows, the solid lines, and also the dotted line as well. The scenario here involves ships communicating with each other at sea using satellite communication, with an emphasis on maintaining communication as ships move. So the primary feature illustrated is the ability for ships to communicate through multiple satellites connected by ISLs, inter-satellite links, without routing the traffic through the ground-based core network. So as ship number 2 moves, it can maintain communication with ship number 1 by switching between satellites facilitated by the ISL. So this is the kind of mobility support between satellites. ISLs allowed for communication over large distances, very large distances, even when ships move out of the coverage area of a single satellite. So using ISLs, the system can route communications very efficiently, potentially reducing latency and improving network performance. So those are the few things we're always after, right? Reduce latency, improving network performance. I don't want to repeat it, but a lot of these configuration have that in mind, that you have to reduce latency and improve network performance no matter how you provide the connectivity and the communication. The ISLs also provide an additional layer of network resilience, allowing for communication paths that don't rely solely on ground station availability because of the capability of switching between the two. It's like a backup. Okay, so this is what is a little bit different from the last one. Okay, next one is the UE satellite, UE2 satellite to UE communication. This form of communication allows UE to communicate directly through satellites without routing traffic through ground-based network infrastructure. This capability is crucial in disaster scenarios, remote expeditions, and maritime and aviation applications, just like the use cases we already looked at just now. It can potentially reduce latency for certain interactions, especially when communicating devices are far apart geographically from each other, but under the coverage of the same or nearby satellites. Challenges include maintaining service continuity during satellite handovers and transitions between satellite and terrestrial networks, as well as maintaining consistent QoS. Implementation requirements include support for various communication types, robust QoS control mechanisms, new approaches to authorization and charging, seamless integration with the terrestrial 5G services, and strong security measures. By addressing these challenges and meeting these requirements, UE to satellite to UE communication can significantly enhance the resilience, reach, the flexibility of 5G networks, opening up new possibilities for global connectivity. So this picture here illustrates the concept of a phone call through one satellite without going through a ground network. What are we looking at here? We have two users labeled Ed, short for Edward maybe, Ed, represented by a blue stick figure on the left. We have Bell. Bell is represented by a green stick figure on the right, or in the middle of the picture here, with an airplane icon nearby indicating they are in flight. We have the satellite. We have one single satellite shown at the top of the image, providing communication coverage. We have a gateway depicted as a satellite dish on the right side of the image. We also have the ground network represented by server icons on the far right. It's labeled as such, ground network. And we have service links, feeder link. There are those dashed lines. We have a network link, also a dashed line connecting the gateway to the ground network. So we have three different links here: service link, feeder link, network link. This picture actually focuses on a call, which is very likely a roaming call. It's represented by a yellow arrow from Ed to Bell, indicating the direct communication path. It is a roaming call. Why is that? Well, the scenario here involves a phone call between the two users via satellite, with one user, Bell, being on an airplane. So when you are being on an airplane, you are likely outside of your home network. The primary feature illustrated is the ability for Ed and Bell to communicate directly through the satellite without routing the call through the ground-based network. Bell is shown to be in an airplane, demonstrating the capability of maintaining communication during air travel. It's in-flight communication. The roaming call label suggests that at least one of the users, likely Bell, because Bell is in flight, Bell is outside their home network coverage area, so it's a roaming call. By allowing direct communication via the satellite, the system reduces latency and improves efficiency, just like the benefits in all of the other use cases. The benefits are pretty much the same. Reduces latency, improves efficiency, a very good use of resources, independence from terrestrial infrastructure. Those are shared benefits in all of these test cases. I'm not going to repeat them in each one of them. So satellite here is functioning as a central node. The satellite here acts as the central node for the communication, receiving signals from both users, which is Ed and Bell, and relaying them without involving the ground network. So in here, the gateway and the ground network, they are present, but they're not utilized for this specific call. Okay, that is how a roaming call is supported by satellite. Next one is multiple communication services between UEs. We have on the picture here a single satellite at the top of the image, providing communication coverage for the area. We have the core network again represented by a cloud icon on the right-hand side, indicating the presence of a terrestrial network infrastructure. We have the communication scenario here is about wildlife observation and rescue operation in a remote area. The locations here, there are three locations. They are labeled as, the first one is labeled as Pride. What it is it's represented by an icon of lions, indicating the wildlife being observed. And then there's the middle one here labeled Camp, with a tent icon representing the base camp for the observation team. There's another tent slightly to its left, is the rescue center, also depicted with a tent and an ambulance icon representing an emergency response facility. The camp is shown to be 2 kilometers away from the Pride. The rescue center is 10 kilometers away from the camp, so we know the distances between these different entities. For communication services, we have 2 different kinds. One is video streaming, a blue line connecting the Pride area to the camp location, indicating live video transmission of wildlife, because this is the application is wildlife observation. And then the next kind of communication service is voice call, a green line. It's green, yeah. Connecting the camp to the rescue center, representing voice communication. For the different kinds of devices, a camera icon near the Pride for wildlife observation, that's a camera. And we also have a device, a display device at the camp location for receiving video feeds. And we have communication equipment at the rescue center for voice calls, let's say. So the scenario is like this. The system supports different types of communication services simultaneously, the video streaming and voice calls in this case. Video streaming demands high bandwidth allocation, and voice calls not so much, lower bandwidth allocation. All communications between the different locations are routed through the satellite without involving the ground-based core network. The scenario here is set in a remote area, likely beyond any traditional cellular coverage, emphasizing the importance of satellite communication. There's no alternative. You can't get to a cellular network. The presence of a rescue center suggests that the system supports critical communications for safety and emergency response, as well as emergency preparedness. The satellite can handle both high bandwidth for video and low bandwidth for voice simultaneously. It has to do that. So this is the use case demonstrating the ability to do so. The 3 locations form a LAN, a local area network, facilitated by a satellite, allowing for efficient communication within the operation area. Again, it's independent from the terrestrial infrastructure altogether. We don't need that in this case. And it is supporting various kinds of applications. So this is one use case. The implementation could be a little bit more complex to support this kind of operations, but certainly it's already being done in the field quite a bit already. So this use case is for collection of information to aid terrestrial network planning. The concept of connectivity and data collection from UEs through satellite access, using satellite communication. So what are we looking at here? We have at the top of the image a satellite access point representing the satellite providing coverage. We have UEs. There are multiple UEs shown representing various devices or sensors in the field. Some UEs are grouped together, indicating they might be in the same geographical area. And then we have this specific UE, a specific or special UE called relay node that acts as a relay for other UEs, extending the network's reach. We have the NTN gateway. NTN stands for non-terrestrial network gateway. This gateway interfaces between the satellite network and the terrestrial network. We have the 5G core represented, just written there in a rectangle, 5G core. We have 5G core. And we have the NMS, the network management system. This is a system for managing and monitoring the entire network. Entire network, meaning the terrestrial as well as the NTN, non-terrestrial. As far as connections go, we have black lines representing wireless connections, likely satellite links. We have red lines representing wired or terrestrial network connections. So this diagram is illustrating satellite access enabling connectivity for UEs spreading across a very large geographical area. Some UEs connect directly to the satellite, while others connect through a relay node, a relay UE, showing flexibility in network topology. The system is designed to collect data from multiple UEs, which could be sensors, IoT devices, or other types of equipment. So it's doing data collection. The diagram obviously here shows a kind of some clear hierarchy from UEs to satellite, then to ground infrastructure. The ground infrastructure here includes the NTN gateway, the 5G core, and the NMS. NMS stands for Network Management System. The satellite access is integrated with the 5G core, allowing seamless operation with terrestrial 5G networks. The keywords here are seamless operation. When it's doing some switching or when it's doing handovers, it has to be seamless. It needs to support service continuity. The network management is included on this picture to indicate the ability to monitor and control the entire network, as I said earlier, including the satellite and terrestrial components. The architecture here supports multiple UEs and can likely scale to accommodate many more devices as needed. So scalability is a component you need to consider when you are designing this use case, this kind of network. The relay node, the relay UE, demonstrates the system's ability to extend coverage and collect data from UEs that might not have direct satellite visibility. This use case is particularly relevant for scenarios such as environmental monitoring in remote areas, agricultural sensor networks across large farms, maritime or desert vehicle tracking, or any IoT deployments in areas with limited terrestrial infrastructure. The next use case is about fleet management in the desert. This is a pretty simple diagram as well. We are looking at an NGSO satellite. NGSO stands for Non-Geostationary Orbit. This satellite provides communication coverage over the desert area. We have the desert indicated by light orange background. That's a big desert. The whole orange part is the desert. We have multiple truck icons representing the fleet of vehicles being managed in the desert. So there's device number 2. That is the relay UE. A device labeled as device number 2 is shown among the vehicles, and it acts as a relay for other devices. We have device number 3. This is another device labeled as such, and is shown separately from the main group of vehicles. Next, core network, represented by a server and cloud icon on the land area, that's on land, indicating the terrestrial network infrastructure. This is showing the management of a fleet of vehicles operating in a desert environment using satellite communication. The desert setting emphasizes operations in areas with little to no terrestrial network coverage. The NGSO satellite provides the primary means of communication for the vehicles and devices in the desert. The system enables tracking and management of multiple vehicles across a wide remote area. So device number 2 acts as a relay, potentially extending the range of communication for other vehicles or devices that might not have direct satellite visibility. Some vehicles communicate directly with the satellite, while others might communicate through the relay device. The satellite provides coverage over a large geographical area, essential for managing widely dispersed vehicles in a desert. The connection to the next core network on land shows how the satellite system integrates with existing terrestrial infrastructure. The system likely allows for real-time tracking of vehicle locations and status. Vehicles and devices can send operational data, status updates, and potentially receive infrastructures via the satellite link as well. The desert setting implies the need for robust communication solutions that can operate in challenging environment conditions. We are talking about very harsh environment operation here in the desert. So what is this demonstrating are that there are key capabilities of satellite integrated 5G systems. The ability to provide connectivity in remote areas where terrestrial networks are not available, for sure, that's one. It supports IoT and M2M communications in wide area scenarios and in harsh operating conditions. Network topology can be flexible, and the integration of both satellite and terrestrial networks needs to be seamless and can be seamless. So this kind of support enable critical business operations like fleet management. All right, so this is an interesting use case in a desert. The next use case is about service differentiation for UEs using satellite access. What are we looking at here? We have a 3GPP NG-RAN next generation radio access network on NGSO satellite at the top of the image. It represents, again, NGSO is non-geostationary orbit satellite with 3GPP next generation RAN capabilities. We have the feeder link, which is a solid line connecting the satellite to the 5G ground station. We have the 5G ground station, which is again depicted as a satellite dish. This is, of course, the terrestrial interface for the satellite network. We have the 5G core network represented by a server icon. This is the central part of the 5G network infrastructure, as we all know. And we have an application platform shown here as a computer and cloud icon connected to the 5G core network. For coverage area number A, a dotted outline encompassing various UE types. For UEs, let's talk about the UEs. UE4 and UE5, represented by house icons, possibly indicating fixed wireless access points or smart home devices. We have UE1 depicted as a truck, suggesting a mobile IoT device or vehicle. We have UE3 and UE2 shown as smartphone icons representing mobile user devices. So the scenario here involves providing differentiated service to various types of UEs through satellite access. You can see that we have diverse UE types. There are different types of UEs we just talked about, including fixed locations, vehicles, and mobile devices, all served by the same satellite network. So we need service differentiation capability. The core concept here is that these different UEs can receive tailored services based on their needs and priorities. The use of a non-geostationary orbit satellite allows for wider coverage and potentially lower latency compared to traditional geostationary satellites. The satellite implements 3GPP next generation RAN standards, ensuring compatibility with terrestrial 5G networks. This is also a hybrid network architecture. The system combines satellite and terrestrial elements with a 5G ground station acting as an interface between the two. The presence of an application platform suggests the ability to run various services and applications tailored to different UE types. And we have flexible coverage. The satellite can provide service to a wide area, including regions where terrestrial coverage might be limited or simply non-existent. The system likely have to implement, and I think absolutely need to implement, QoS mechanisms to prioritize traffic based on UE type and service requirements. Scalability is a concern. The architecture supports multiple UEs of different types, indicating scalability to accommodate diverse use cases. Okay, so this is one interesting use case. The next use case is about service continuity for UE to UE communication between satellites. We have 3 different frames here. Let's take a look at the elements quickly. We have NGSO satellites. There are 2 non-geostationary orbit satellites, SAT-1 and SAT-2, SAT-1 and SAT-2, are shown moving across the top of each frame, each of these 3 frames. We have 2 firefighters, A and B, are depicted in a deep forest area, maybe fighting forest fire, representing UEs. We have a ground network, again represented by a satellite dish icon, and that's the terrestrial network infrastructure. The colored lines are the communication links, showing the communication paths between the firefighters and satellites. So this 3-stage process of maintaining communication between 2 firefighters in a deep forest area as satellites move ahead, that's the scenario we're looking at. Let's take a look at stage 1, the left frame. Both firefighters are communicating through SAT-1, which is the blue satellite. The communication link is represented by blue dashed lines from each firefighter to SAT-1, satellite 1, with a red solid line between them indicating active call or data exchange. SAT-2, satellite 2, which is the green satellite, is visible but not yet in use. In the middle frame, the stage 2 middle frame there, as the satellites move, SAT-1 is still the primary communication link for firefighter A. Firefighter B begins transitioning to SAT-2, shown by the green dashed line. The call or data exchange continues uninterrupted, represented by the red solid line now curving between the 2 satellites. On the right frame, the stage 3, the transition is complete. Firefighter A now communicates through SAT-2, satellite 2, the green satellite. Firefighter B has fully transitioned to SAT-2. The call or data exchange continues, now entirely routed through SAT-2. What this is indicating is a seamless handover. The diagram demonstrates how communication is maintained as satellites move and UE transition between them. So there is an implementation of seamless handover, which is not easy to implement correctly and efficiently, but yet it's a requirement. The firefighters communicate directly through the satellites without routing through the ground network. So this is direct UE to UE communication. The use of moving GNSO satellites between the constellation showcases the dynamic nature of the network and the need for continuous handovers. The deep forest setting highlights the importance of satellite communication. In areas without terrestrial network coverage. So it is covering very remote areas, like in the deep forest. The firefighter scenario emphasizes the use case for emergency services. As you can imagine, firefighting is an emergency, and critical communications. The middle frame shows how two satellites can coordinate to maintain a single communication link during transition using what? Inter-satellite link, doing inter-satellite coordination. Okay. Next one is similar to the last one. This one illustrates the concept of service continuity for UE to UE communication in case of mobility between satellite and terrestrial network without going through the ground network. We have a single satellite shown in both frames. We have two UAVs, unmanned aerial vehicles, labeled as Vehicle A and Vehicle B. We have the ground network again depicted by a satellite dish and cloud icon. We have the terrestrial network shown here as a separate entity with its own coverage area. Red lines indicate active communication, blue dashed lines for satellite links. The diagram shows here is a two-stage process, maintaining communication between two UAVs as one moves from satellite coverage to terrestrial network coverage. Stage 1 on the left frame, both UAVs, Vehicle 1 and Vehicle B, are within the satellite network coverage area. They're communicating directly through the satellite, as shown by the red line passing through the satellite. Vehicle B is near the edge of the satellite coverage area and close to the terrestrial network coverage area. Stage 2 on the right frame, Vehicle A, remains in the satellite network coverage area. Vehicle B has moved into the terrestrial network coverage area. The communication link, the red line, now shows a direct connection between the two UAVs, bypassing both the satellite and the ground network. So this is showing again another seamless transition. The diagram demonstrates how communication is maintained as one UAV moves from satellite to terrestrial network coverage. The UAVs maintain direct communication without routing through the ground network, even when on different network types. So you're seeing direct UE to UE communication. The use case here again showcases the interaction between satellite and terrestrial networks in providing continuous coverage. This is again a hybrid network scenario. This is providing mobility support for sure, because the vehicles, the UAVs, are moving, and the scenario highlights the system's ability to handle both vehicles transitioning between different network types. So this is mobility support that is being provided. The UAVs can utilize either satellite or terrestrial networks based on availability and precision. So this is, again, providing flexibility in network access. Okay, let's take a look at GNSS, which, as you know, stands for Global Navigation Satellite System. GNSS, independent operation and positioning enhancements. And these enhancements are crucial for scenarios where GNSS is insufficient or unavailable. This includes indoor locations, urban canyons, and areas subject to GNSS outages or interference. By developing GNSS-independent methods, 5G systems can ensure continuous positioning services in challenging conditions and support devices without GNSS capabilities. 3GPP is exploring various positioning methods for satellite access, including TDOA, we'll take a look what that is, AOA, hybrid positioning, and enhanced cell ID methods. So TDOA is time difference of arrival. AOA is short for angle of arrival. These techniques aim to provide accurate positioning across diverse environments. Performance considerations include varying accuracy requirements for different services, improving availability in challenging environments, reducing latency for real-time applications, ensuring power efficiency for battery-operated devices, and maintaining scalability for high volumes of positioning requests. These enhancements will significantly improve the reliability, availability, and versatility of location-based services across a wide range of applications and environments. Let's take a look at other aspects of satellite access. Efficient communication paths are essential for optimizing the performance of satellite integrated 5G networks. This involves developing intelligent routing algorithms, load balancing across multiple satellites and ground stations, and minimizing latency for delay-sensitive applications. The collection and analysis of usage statistics play a vital role in ongoing optimization and management. This includes monitoring resource utilization, tracking usage mobility patterns, analyzing traffic patterns, and gathering data for regulatory compliance. Security is paramount in satellite communications. This includes implementing robust end-to-end encryption, strong authentication mechanisms, protect against signal spoofing and jamming, and ensuring data privacy across international coverage areas. By addressing these aspects, satellite integrated 5G networks can offer reliable, efficient, and secure communications across global coverage areas, opening up new possibilities for connectivity in previously underserved regions and scenarios. What about charging? Very important here, charging aspects for satellite services. Charging for satellite access services in 5G systems presents unique challenges. For SNF operations, store and forward operations, charging models need to account for data storage duration and differentiate between immediate and delayed transmissions. Multi-hop satellite routing scenarios add complexity to resource usage calculations. UE to satellite to UE communication charging introduces the concept of direct billing for peer-to-peer communication facilitated by satellites without ground network involvement. The system must differentiate between various types of communications and handle scenarios involving multiple satellite hops. Roaming considerations include inter-operator charging for satellite services, handling charges for UEs in international waters or airspace, reconciling charges across different satellite operators, and ensuring compliance with international roaming agreements. It gets more complicated as you think about it. These charging aspects require innovative approaches to ensure fair, transparent, and economically viable billing models for satellite integrated 5G systems. All right, this is the second to the last slide, talking about the consolidated requirements which represent the culmination of our analysis across various use cases and scenarios so far. For store and forward operations, we've identified the need for flexible, secure, and efficient data handling, including configurable retention periods and storage quotas. UE to satellite to UE communication requirements focus on ensuring seamless and versatile service, including support for various communication types and maintaining service continuity as satellites move. Positioning and GNSS independence requirements reflect the need for reliable location services in all scenarios, including developing 3GPP-specific positioning methods for satellite access. Security requirements underscore the importance of protecting user data, including end-to-end security, robust authentication, and protection against spoofing and jamming. Charging requirements address the need for flexible models that can handle the unique aspects of satellite communications, including roaming and inter-operator scenarios. These consolidated requirements provide a comprehensive framework for integrating satellite access into 5G systems, addressing technical, operational, and commercial aspects of this complex integration. All right, as we conclude this study on satellite access phase 3, it's clear that the integration of satellite technology into 5G systems represents a significant leap forward in mobile communications. Our key findings demonstrate the viability and importance of features like store and forward operations, UE to satellite to UE communication, and GNSS independent positioning solutions. These advancements are crucial for the future development of 5G networks and 6G networks. They pave the way for truly global coverage, extending 5G services to remote areas, oceans, and airspaces previously unreachable. The enhanced network resilience and reliability offered by satellite integration will be critical in emergency scenarios and for maintaining communications in challenging environments, like in a desert. Looking ahead, the next steps in standardization are clear. We need to develop detailed technical specifications based on the requirements outlined in this study. Further research into performance optimization, particularly in areas like latency reduction and resource management, will be essential. Thank you for watching, and I hope to see you in the next 3GPP presentation. Goodbye.